In this video, you learn how your cells produce energy, what the energy systems are, how they are interconnected, which organs are responsible for which energy systems, how different muscle types correlate with these systems, how our body shifts gears between energy systems, and finally, which type of training works best for each energy system. Crazy amount of information, all interconnected and structured so that you get the full knowledge of your body. Let's dive in. How do we produce energy? Our body consists of trillions of cells, and each one generates energy in the same way, by using ATP. ATP is a molecule with 3 phosphate groups. The bonds between these groups store significant energy. When one phosphate group is ripped off, it releases energy for the cell to use. And this is exactly what each of the cells of our body do. Someone provides them with ATP, they rip off one phosphate group and get a decent amount of energy. The question is, who provides ATP to the cells? The body has over 20 different ways to create ATP, but the 4 main pathways are Creatine Phosphate System, Glycolysis, Aerobic Respiration, Fatty Acid Oxidation. Each of these processes involves numerous steps, but we would focus only on the basics. Simplest one is the creatine phosphate. Phosphocreatine donates a phosphate to ADP, producing 1 ATP. It happens instantly, making it the fastest source of energy, but the downside is that the body only has a small amount of phosphocreatine, so it depletes within 15 seconds. The second pathway that we will explain is fatty acid oxidation. Fats, which we have plenty in our body, come through many circles of beta oxidation. As a result, we get a lot of acetyl-CoA and special fuel. Acetyl-CoA then enters the Krebs cycle, generating more special fuel and ATP. All collected special fuel goes to the electron transport chain, where under heavy fire of protons, phosphate is connected to ADP, producing ATP. Overall, one fat molecule generates about 106 ATP. Next two are complicated and connected. In fact, they almost could be considered as one because the outcome of glycolysis is the starting position of aerobic respiration. So the aerobic method, aerobic respiration, cannot exist without anaerobic method glycolysis. However, glycolysis can exist on its own, so we need to keep 2 lines. First, let's cover full cycle. Glucose is converted into pyruvate, which produces 2 ATP, water, some special fuel, and protons. Next, pyruvate is converted into acetyl-CoA, again producing some special fuel and some CO2. The Krebs cycle then takes acetyl-CoA, producing more special fuel. Finally, the special fuel enters the electron transport chain, where they donate electrons and protons. As a result, we get 28 ATP, water, and heat. Thus, from a full cycle of glycolysis and aerobic respiration, we get 32 ATP. Pretty impressive. However, sometimes our body struggles to deliver oxygen, which blocks these processes. In that case, the way the body can get ATP is through glycolysis. Even though glycolysis produces only 2 ATP, it is a faster energy method than aerobic methods. And a valid question would be, why would we even need aerobic methods? Well, at some point you run out of NAD+, and you need NADH to be converted back to it to proceed with glycolysis. This is where your body developed a mechanism to get NAD+. Pyruvate is converted to lactate. And please don't worry about lactate. It's a helpful byproduct that can be converted back to pyruvate anytime with almost 0 energy input. Issue of glycolysis, that on top of pyruvate, it produces a lot of protons. Protons make the muscles more acidic, leading to the burning sensation often felt during intense anaerobic exercise. And the more we go through the cycle of pyruvate production, the more protons we generate, the more blocked our muscles are. Why then do athletes measure lactate instead of acidity to study how bad the situation in their body is? Because there is no convenient way to measure acidity, while lactate level is highly correlated with acidity. And this is where the myth that lactate blocks muscle is born. Anyhow, we finally got to the interesting part of the video. Let's do the comparison. We have 4 sources of ATP. The main limitation for 2 of them is oxygen. Without it, they won't function. The limitation of the creatine phosphate system is that there is only a small amount of creatine phosphate available in the body, so it doesn't last long. As for glycolysis, its limitation is it produces a large number of protons, which make the environment more acidic, and therefore it also cannot last long if we use it on a maximum capacity. However, it is more important how much we produce. Per one cycle, we get 1 ATP with creatine phosphate system, 2 ATP with glycolysis, roughly 30 ATP with aerobic respiration, roughly 106 ATP with fatty acid oxidation. So you clearly see that fats is most energy-rich process. People with a lot of fats have higher energy potential. Not only do they have more cells than others, but also each cell can produce more energy. However, that also may be the reason why it is hard for them to get into shape. Just imagine how much energy they need to spend in order to burn through such reserves. The second thing we need to compare: speed of production. I need to note that in this example, we will neglect all limitations of fuel shortage and other restrictions. Let's take an imaginary world where it is true. Creatine phosphate system can produce 12,000 ATP in an hour. Glycolysis can produce 7,200 ATP in an hour. Aerobic respiration can produce 4,500 ATP in an hour. Fatty acid oxidation can produce 2,500 ATP in an hour. And now you understand that actually the creatine phosphate system is superior. You can instantly create much more energy with this method. It will last only like 15 seconds. You only have one shot, one opportunity. Think about it when you will participate in some form of competition next time. But what about some realistic scenarios? What about how many ATPs can we realistically produce in an hour? Creatine phosphate system can produce 350 ATP in an hour. Glycolysis can produce 1,200 ATP in an hour. Aerobic respiration can produce 4,500 ATP in an hour. Fatty acid oxidation can produce 2,500 ATP in an hour. Now you see that actually aerobic respiration is the most efficient method. It does not have time limitations like glycolysis. Also, it is pretty fast compared to fats or protein. Basically, each ATP production method has its strengths. Some are fast, some are more efficient. All methods are valid, but I believe you might not fully understand what to do with all of this information. How do you use these methods in real life? In order to understand that, we need to draw a graph of the possible ATP production over time with each method. For example, for creatine phosphate, we said it only works for 15 seconds. Then this is the creatine phosphate over time graph. One note that all previous calculations were made for one cell. At this point, we need to switch for the whole muscle. That means that we cannot really use previous numbers and rather operate on the same scale. Also, to make it a bit more accurate, let's rename ATP volume to power, because for us it is important how much power we can produce. So the graph shows the relationship between the power we can achieve during an exercise and the duration of the exercise. We already discussed creatine phosphate, which could produce a lot, but only in a short period of time. Glycolysis can produce a bit less, but for longer. It is limited due to excessive protons and lactate production. Aerobic respiration takes a bit more time to start working. However, after about 3-minute mark, it is the biggest source of ATP production, since other sources have limitations. To be fair, we only have about 2 hours of glucose storage in our body. Yes, we can eat during exercise and restore around 100 grams per hour, but let's neglect it for the moment. Our fat's capacity, however, is almost unlimited, but we only can produce a small amount of power from it. Now you see the pattern. Let's draw the graph of the maximum possible power output over time. It looks something like this. For each individual, it varies. Some are sprinters who can generate high power for short durations, while others are endurance-oriented, maintaining a steady output over longer periods. Why are they like this? Because they have different combinations of ATP production sources developed. Sprinters have developed glycolysis, while stayers have developed fatty acid oxidation. Worth noting that this graph is only about maximum effort. For sure, we could make less effort on our exercise and produce only, let's say, this much amount of power. Do we have some examples? Yes. During short races, you can run much faster than during long races. That is because you can produce more power over a short period of time. Good examples for this are world records for different running distances. If we compare the speed of running, which actually represents power, we see that the longer the distance, the slower the speed. So this would be your across all elite athletes' maximum possible power over time graph. Now you know methods of energy production and which are better for what. One can give you burst in short races, other in long races, and here is some useful knowledge. First, we can actually train different ATP production methods. This means, for example, if we want to increase endurance, we can enhance our aerobic respiration. On the other hand, if we want to become sprinters, we can improve the efficiency of glycolysis, leading to a higher power output in shorter exercises. Second, the more we increase glycolysis, the more we limit aerobic respiration, and vice versa. The more we increase aerobic respiration, the more we limit glycolysis. This will be explained in the muscle types subsection a bit further. Keep in mind, I said limit. Most likely, this video is being watched by beginners, whose levels of aerobic respiration and glycolysis are still relatively low, so they can easily develop both. By now, you likely feel confident in understanding energy production methods. However, to effectively develop these systems, it's essential to understand where they occur and which organs and structures are involved. Let's break this down. The creatine phosphate system operates in the sarcoplasm. To enhance this system's efficiency, you need to increase your creatine phosphate reserves. This will provide more immediate energy for short bursts of high-intensity activity. Glycolysis also takes place in the sarcoplasm. To improve its efficiency, you should focus on building larger glycogen reserves. On average, the human body stores about 400 grams of glycogen in muscles, approximately 15 grams per kilogram of muscle mass, and an additional 100 grams in the liver, which serves as an emergency reserve. Interestingly, this is why predators often target the liver first. It's the most energy-rich organ in the body. Next is aerobic respiration and fatty acid oxidation. These two are a bit more complicated. First of all, both of them occur in a special place within a muscle cell called mitochondria, and the more you have them, the more ATP you can produce. Glycogen and fat reserves are not the limiting factor. Instead, these systems are heavily reliant on oxygen. Let's explore how oxygen is delivered and consumed. Oxygen enters the body through the lungs during breathing. You would expect that we tell you that you need efficient lungs to consume more oxygen, but that is not the truth. Usually, lungs are not a limitation. They produce enough oxygen. However, further steps of delivering oxygen to the muscles are lacking capacities. This is why devices like lung training masks are largely ineffective. They address a step, which is not a limitation for most people. Next step is your blood quality. Specifically, how much blood you have and how much oxygen it can carry. Amount of blood is referred to the number of red blood cells, while the hemoglobin amount refers to how much blood cells can carry oxygen. And please be aware that too much hemoglobin is not good. Excessive hemoglobin thickens the blood, slowing circulation and raising the risk of blood clots. Also, it is really hard for such blood to reach well-developed small capillaries. Usually, blood is a limitation. For example, your lungs might supply 100 units of oxygen, but if your blood can only transport 80 units, oxygen delivery is limited. Yes, you feel that you need more oxygen, you're suffocating, but it is not because you are under-breathing. It's because your blood is not delivering. Next component of oxygen delivery is the heart, which is the pump for our blood. A strong heart pumps more blood, ensuring that oxygen reaches muscles effectively. The heart is arguably the most critical muscle in the body, but I will speak about the muscles just a bit later, so it makes sense to come back after that. Next is the number of small capillaries surrounding your muscles. It determines how efficiently oxygen can be delivered. A dense capillary network allows for better oxygen supply, but may reduce available space for muscle fibers. Balancing capillary growth and muscle development is crucial for optimal performance. Next, our muscles consume the oxygen. First step is myoglobin, which acts as a warehouse inside sarcoplasm. It stores oxygen for periods of high demand. Increasing myoglobin levels enhances the muscle's capacity to absorb oxygen. Finally, mitochondria serves as ATP factories. All processes involving aerobic respiration and fatty acid oxidation occur here. The more mitochondria you have within your muscle cells, the more you can use aerobic respiration and fatty acid oxidation. So these are all organs and structures involved in energy production. But we forgot about one extra player, the one who will be consuming all the ATP, microfibrils located inside muscle cells. They will be doing the work, while the rest we mentioned are only warehouses and factories of fuel. And now let's do a couple of imaginary muscles. Imagine your muscles have large reserves of creatine phosphate, vast glycogen stores, huge amounts of myoglobin and mitochondria. It sounds perfect, doesn't it? But there's a problem. Despite the robust ATP production systems, you don't have enough myofibrils to perform the work. This setup is inefficient in real life because myofibrils must occupy at least 50% of the space to ensure effective muscle performance. Now imagine a muscle with only a few mitochondria and minimal myoglobin, but great glycogen reserves. The rest of the space is packed with myofibrils. This muscle type mainly relies on glycolysis for energy. Since glycolysis is fast, such muscles provide quick bursts of energy and increased strength due to the abundance of myofibrils. This setup is ideal for sprinters. It offers speed and power. However, the lack of mitochondria means the muscle fatigues quickly and recovery takes longer. These examples illustrate how muscle type depends on its internal composition. And let me jump straight to the point. We as humans have 3 options of muscle fibers. Slow twitch fibers. These have more myoglobin and mitochondria, but fewer myofibrils. They are designed for endurance, working for long periods but producing less power. Fast twitch fibers. These have abundant glycogen reserves and myofibrils. They provide quick, powerful movements but lack fatigue resistance. Intermediate fibers. These are a middle ground offering moderate endurance and power without excelling at either. Next thing you need to learn is that you are born with a unique combination of slow, fast, and intermediate muscle fibers. Some people naturally have more fast twitch fibers and tend to excel in sprinting, while others have more slow twitch fibers and perform well in endurance events. Can you, with your combination muscle fibers, change something? Well, first of all, you can train, and if you put into work fast twitch fibers, they will grow. Same with slow. If you mostly will do aerobic jogs, they will grow. If we take identical twins and train them differently, one might develop as a sprinter, while the other excels as an endurance athlete. But can you change one type of muscle fiber to another? It's incredibly difficult. It will take a lot of training just to change a small amount. However, we can change intermediate to fast, intermediate to slow, fast to intermediate. However, these changes require consistent high-intensity training over a long period. Alright, let's recap what we just learned. All our cells get energy from ATP. Our body has 4 mechanisms to produce it. Some are faster, while others are more efficient. We explored which organs and structures are required to activate each mechanism. We also learned that developing one organ or structure can compromise another or reduce muscle strength, as the limited space within muscle cells prevents accommodating everything we might want. Finally, we examined the types of muscle fibers, which are essentially different combinations of the organs and structures necessary for various ATP production methods. This knowledge is the base. However, there are a few more things you need to know. Let's make a timeline. What is happening with your body when you do harder and harder exercises? First of all, at any exercise intensity, all energy systems contribute. However, depending on the intensity, your body prioritizes certain systems. During low-intensity exercise, your body primarily burns fat, the most energy-rich resource. As long as the intensity is low enough, this fuel source is sufficient to meet your energy needs. When fat burning alone cannot provide enough ATP, the body activates glycolysis and aerobic respiration. This stage is known as the first lactate threshold. At this point, glycolysis begins producing lactate, but aerobic respiration efficiently consumes it, preventing lactate and excessive acidity buildup. As intensity increases, lactate production via glycolysis surpasses the capacity of aerobic respiration to utilize it. This is the second lactate threshold. Here, muscle acidity rises rapidly, limiting how long you can sustain this intensity. You may notice that aerobic respiration is still not maxed out here. In this area, lactate accumulates faster than it can be utilized, not because aerobic respiration is maxed out, but because it is too slow to meet the immediate demand for ATP. For example, if your body needs 8,000 ATP molecules instantly, aerobic respiration might only provide 5,000. This delay forces your body to rely on faster, less efficient energy systems. The next stage is when aerobic respiration reaches its absolute limit. It is the point where we hit the limit of our oxygen supply, also called VO₂ Max, point where we max out capacities of all organs involved in oxygen production. Beyond VO₂ Max, all energy systems operate at their maximum capacity. Now you understand the breaking points, but you might still wonder how to apply this knowledge or identify where you are during exercise. This is where heart rate comes into play. Heart rate correlates directly with exercise intensity. The higher the intensity, the higher your heart rate. Heart rate zones, which you may already be familiar with, represent different combinations of energy systems at work. To determine the precise heart rate at your breaking points, a lab test is necessary. However, most smartwatches provide fairly accurate estimates, so you can rely on them for practical purposes. Lastly, athletes include an additional zone in their training, the recovery zone. This zone is intentionally set at an intensity level where none of the energy systems are maxed out or approaching a breaking point. It's not aimed at improving energy systems, but instead focuses on relaxation, muscle tuning, and recovery. The key to improving a particular energy system lies in fine-tuning your training intensity. To answer the question, how do I improve my specific energy system? You need to train at the maximum capacity of that system. This sends a clear signal to your body that it must adapt and grow stronger. For fat metabolism, the optimal intensity is at the first lactate threshold. For aerobic respiration, it's at the second lactate threshold. For glycolysis, you need to train at VO₂ max intensity. And remember, recovery occurs in zone 1, where no significant improvement happens. Before diving into specific training types tailored to each system, let's focus on the relationship between VO₂ max and the second lactate threshold. Many endurance athletes obsess over VO₂ max, striving to increase this number. However, training excessively in this zone primarily develops glycolysis, which can limit aerobic respiration. It means you are limiting your endurance, opposite of what endurance athletes are looking for. Second example would be, you are really focused on developing aerobic respiration. You are increasing your second lactate threshold, but at some point it hits your VO₂ max, which is low, because you never tried to develop it. Then you are also not really well developed for endurance. The second lactate threshold reflects the efficiency of your oxygen consumption system, which involves mitochondria and myoglobin inside the cells. VO₂ max, on the other hand, measures the capacity of your oxygen delivery system, including your heart, blood, and capillaries. Both systems are crucial for overall performance. These examples highlight the importance of a balanced, well-designed training plan to achieve optimal growth. But first, you need to understand what is limiting you. Is it not a well-developed oxygen delivery system, which stands for VO₂ max, or oxygen consumption system, which stands for second lactate threshold? One more pretty important point is about weight loss. Many of you might be thinking, to lose weight, I need to train in the fat-burning zone. Unfortunately, this is a common misconception. The truth is, weight loss happens when you consume fewer calories than you burn, no matter how and where you train. When you train in the so-called fat-burning zone, all you're doing is teaching your body to improve its fat-burning efficiency during exercise. I repeat, during exercise. Let's look at an example. You can train in zone 4 for 10 minutes, and then to recover, your body will burn an incredible amount of fat. Or you can train in zone 2 for 10 minutes and burn some fats. However, your recovery will not be that big. So actually, it doesn't really matter which workout you choose. You need to eat less than you burn. This is the only way to lose weight. Now let's talk about training types and how they help develop different energy systems. In general, we have 4 common types of training: recovery run, easy tempo run, fast tempo run, and intervals, or fartlek, on hill climbs. I need to remind you that to develop any energy system, you have to push it to its limits. And I think by now you already have a good sense of which training improves which system. A recovery run doesn't directly impact any energy system, but it's still valuable. Outside of energy systems, there are other areas we need to develop. However, just doing recovery runs won't make you faster or improve your endurance. A basic steady run is focused on developing your fat-burning system. This is why endurance athletes spend so much time in this zone. As you remember, fats are virtually unlimited, while glucose lasts only around 2 hours. That means most people run marathons using fat for fuel. And I'm not even talking about ultra marathons here. Also, increasing the number of mitochondria benefits not just fat burning, but also aerobic respiration. A fast tempo run focuses on aerobic respiration. It helps you balance glucose consumption through glycolysis and mitochondrial activity. Intervals, on the other hand, push the limits of your body. where aerobic methods aren't enough. This develops your glycolysis, but it also develops your VO₂ max, which is still very necessary for aerobic systems. My examples are simple, but even intervals can be broken down into 3 or more types, each targeting different aspects of your body. But that's a bit much for today. This is exactly what we do for our athletes in the Run FAQ running school. If you really want to learn more, the best way is to experience it firsthand by training with us. With that said, I just want to quickly sum everything up. Each cell in our body gets energy from ATP. We have 4 main ways to produce ATP, and each method has its own advantages and disadvantages. We can choose which one to develop, and based on that choice, we either become more enduring or faster. When we focus on developing a particular method, we're also developing specific structures in our body. For example, muscle types are linked to the energy systems they rely on. We also learn how our body selects its energy production method based on workout intensity, and how heart rate zones correspond to gears in this system. Finally, we went over the different training types that develop each energy system. I think that's more than enough for one video. I'm sure I messed up somewhere, so feel free to leave a comment. Bye-bye.